Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the adiabatic flow with friction. During fluid flow through many devices such as ladles, diffusers, and turbine blade passages, flow quantities vary primarily in the flow direction only, and the flow or the process is irreversible and adiabatic. With the same pressure drop compared with the isentropic flow at the ladle outlet, the gas entropy increases, the temperature and enthalpy increases, and the flow velocity outlet decreases due to the friction. The velocity coefficient and the ladle efficiency will be discussed for the frictional adiabatic flow in ladles in this task. To analyze the adiabatic flow with friction, two assumptions are made. The fluid is ideal gas with constant heat capacity. The frictional adiabatic flow is polytropic process. We have the following equations for the frictional adiabatic flow in ladles. Firstly, the energy equation is. Secondly, the momentum equation is. Thirdly, the equation of state is. Fourthly, the process equation is. Fifthly, the sonic speed is. And finally, the continuity equation is. Starting with the energy equation, we have. This indicates the variations of temperature and velocity have same trend. Starting with the polytropic process equation, we have. This indicates the variations of specific volume and velocity have opposite trend. Substituting the above equation to the continuity equation, we have variation relation of flow area and velocity. At the throat of a converging diverging ladle, we have, since the polytropic exponent is less than the specific heat ratio of ideal gas, then the Mach number is less than unity at the throat for the frictional adiabatic flow. This means the flow velocity at the throat is subsonic when there is friction. When the Mach number is unity, we have positive area variation. The critical section where the Mach number is unity occurs at the diverging part downstream the ladle throat. Starting with the energy equation, we have velocity for ideal gas with constant specific heat and can be further expressed as. Starting with the polytropic process equation, we have equation 935, another form for velocity. Please compare this equation with equation 922. Can you find the differences between them? Then, from equation 935, the critical velocity is. With the definition of sonic speed, the above equation can also be written as. We then have this relation. Substituting paratropic relation, we then have the critical pressure ratio. Similarly, we have the critical temperature ratio or the critical density ratio. These three critical ratios are very useful for practical compressible flow calculations involving air. Then, the critical velocity has the following expression. The critical velocity for the friction flow is found identical to that of frictionless flow as shown by equations 926 and 940. Okay, that's all for this task. Thank you very much and see you next time.